Hello everybody. In our previous class we discussed various different type of notations, BCD number representation in binary or text representation or any other symbol representation. So today what we are going to discuss is, can we represent real numbers in binary or not? In our first lecture we understood that digital numbers are discrete. Okay, so discrete means they're not continuous. Now, can we use these discrete numbers to represent continuous numbers like real numbers? In world around us, actual numbers are both integers as well as real numbers. Integers means counting 1, 2, 3, 4, 5, but real numbers where fractions are also there. Now, can we represent numbers that contain both fractional part and integer part, or essentially we call them real numbers? So can we represent using binary, can we represent real numbers? You will say, of course, yes, because in even in our one of the previous class we have seen that how a fractional part can be represented. We took various examples and you also gave in class quiz around that. So that means that can be done. Now, but the major point again, the major point here is, or the most difficult point which we have to understand and see, is that how to represent this decimal point. You see, in binary, as we have seen earlier, that this decimal point we can only have zeros and ones. Now this decimal point is also has to be represented either using 0 or 1, or we have to fix a point, we have to fix the precision. We have to say that okay, only 10 digits after this decimal point will appear only after 10 digits. Okay, so this decimal point has to be represented. Now this fixed point, or one way of representing this decimal point, is that we don't write decimal point per se, but there is an agreement between a reader and writer, person who is giving the binary number and who is reading this binary number. Now when this agreement is there, that means we are saying that there is a point which exists. So let's take this with an example. So let's say we have a 4 decimal digit number, okay, and we say that the point will always exist only after 2 points. So that means, let's say we have a number 2300, and because in a fixed point notation we said that the decimal point will exist after 2 digits. It's not written over there, but it is implicitly assumed because there is an agreement. There is agreement between a reader and writer, whoever is writing this number. For example, you are writing 2300, but because there is an agreement that decimal point has to be considered after 2 digits, so that means this number, whoever is reading, he will understand the number is 23.00. Similarly, if 123 is given, then because decimal point would exist after 2 points, after 2 digits, then it would be 1.23. It would be read as 1.23, although it is written as 123, but because of that agreement that there is a point which exists but which is invisible, you don't see that. So this could be one way of representing a decimal point without writing a decimal point. I would again like to rephrase this question also. What question we are solving? Because decimal point also need to be represented as 0 or 1. We have only 2 symbols. In decimal system, in decimal system we invented one more symbol. So initially there were 10 symbols, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then because we wanted to represent, we wanted to write a real number, so we invented one more symbol called dot. So because of this dot, now there are total of 11 symbols. Because of this dot we are able to represent real numbers also. But in case of binary we don't have that choice. So this decimal point, either we assume that it exists or we have to use 0 or 1 for representing decimal. So that thing is a challenging thing, that how we can represent this decimal point. So the representation where we are assuming this assumption, let's say we are taking an assumption that this point, decimal point, occurred at this particular digit place, then you cannot violate that agreement. All the numbers who are following that agreement will always put the decimal point at that place. That cannot change with the program. So let's say your program is executing for 1 hour or maybe for multiple days, then this representation of fixed point will always remain for all the numbers. Okay, and yeah, so total number of digits will also remain same. So these are the some constraints which are imposed on fixed point. Okay, so if you look at the other way, so let's say you are looking at this number 23.00. So this 23.00 is effectively multiplied by 100 and then written as 2300. So whenever I am writing, I am multiplying, because of decimal is exist after 2 digits, so I am multiplying it by 100. If decimal point exists after 3 digits, then I would multiply it with 1000. So effectively whenever I am writing, I am multiplying it with some particular factor, and whenever I am reading 2300, so I would divide it by 100, so I will get that 23.00 is the actual notation. Or if number 1 is given, then I had to divide it by 100, so it will become 0.01. So in this way we can represent binary numbers also. This was the example of decimal numbers. So in the similar way, in binary numbers also we can represent this point. Now let's take an example of binary numbers. So let's consider that we have a 16-bit number. This number could be actually 32-bit number or any number, but let's say we are fixing the size of our number as 16-bit number. For sake of completion, we will see that the maximum range of the 16-bit number would be 0 to 65,536 if the number is considered as completely positive. It is not, it doesn't have signed representation, only unsigned representation. And if we are representing signed numbers also, then in 2's complement the range is minus 32,000 to plus 32,000. Okay, so this is the range if there is no decimal point, if the number is either completely positive or it has some negative part also. Now let us say we have a decimal point. So where we'll put decimal point, that is also a question. So let us assume that we are putting a decimal point after 4 binary digits or essentially after 4 bits. So after 4 bits, if we are assuming there is a decimal point, again try to understand, it is only an assumption. Assumption means there is no explicit, this binary point is implicit, and it would be understanding of whoever is reading and whoever is writing. So let us say my binary point is assumed at this location where 4 bits, that means 0, 1, 2, 3 will form the fractional part, and bit number 4 to 15 will form the magnitude part. Now this means that I have reduced the number of bits representing magnitude from 16 to 12. So that also means that the range will be reduced I can only represent, if it is a this is a signed number, that means I can only represent instead of 32,000 I can represent only 2000, minus 2000 to plus 2000 numbers, and only 4 bits of fraction. 4 bits of fraction means that one of the 16 levels. So whatever is the fractional part, we will divide them into 16 parts and we will see that which 16 part we would like to take. So that means this number is precision is very less. Okay, so after decimal only, if I convert into a decimal number, then effectively only one digit after decimal point, one decimal digit after one decimal point, too less. So if I want to increase the precision, I have to move this decimal point to, let's say, some other place, let's say after 8 bits. If this 8 bit, after I am putting this decimal point after this 8 bits, the range of number is further squeezed. I can only represent from minus 256 to 255, very less. Okay, and the fraction is also 8 bit, which is also less. Okay, so that means a fixed point representation could be a good possibility, but there are multiple issues. One issue is that it will reduce the range of numbers which I can represent, and also precision is not that great. The amount of, like, a number of bits I can use for fractional part would be severely limited by the size of my number. Okay, and because I would always if I want to, for example, here the smallest number I can represent is 1, which means that it would be 0.00000001. Okay, so the size of number is also quite less. It depends on the number of bits I am using. If I increase the number of bits, that also doesn't solve the problem much. Okay, so that means there has to be some better solution. Still, these fixed point numbers are preferred in at least some part of computation. They are very important. We can't simply ignore them. So we'll see later, if we use some other method, then the computation, addition, subtraction, multiplication is a very complex operation. But here I can assume all of these numbers, fixed point numbers, as integers and do all the computation assuming they are integers, and then some correction factor can be applied over it, after it. So that is the biggest advantage of these fixed point numbers, that you might have heard that like in lot of computational programs, like in machine learning and all, so initially all the floating point numbers, or that complex format which we are going to discuss in our next slide, were used, but because it was computationally so heavy that people said we will lose the accuracy, but because computation time would be less, so we can move towards fixed point format. So that means a fixed point format in a sense can give us a faster computation, but with very less accuracy, because precision is very less. Number of bits that can be represented after decimal is one. First thing, it is fixed. The other thing, they are also limited and small in number. So that means we need to find some other method to represent these real numbers. And also there is one more reason to represent these real numbers. So these real numbers are not only represented just to have this fractional part and magnitude part, but also they help us in representing very, very large numbers. So for example, if we see what is the mass of Earth, weight of Earth, it is approximately 5.972 into 10 is to power 24 kg, quite large. Now if I want to use I want to consider this as an integer number. Okay, if I want to consider this as an integer number of bits I would require just to represent this number would be more than 80. So that means the format which we have, 32-bit integers or 64-bit long, they will not be able to contain this large number. I have to have something which would be, for example, 128 bits to represent this number. So to represent large numbers, and this is one of the large numbers, there could be so many things around us which represent quite a large numbers. So for example, if you see this is another example from your chemistry. If you see number of atoms in 1 gram of hydrogen, you call it 1 mole, Avogadro numbers, 6.02 into 10 is power 23. So many zeros are there. So that if I want to represent them, if I want to represent them in integers, that means number of bit required would be large. So there are other examples of even bigger numbers which are like in the world of computation. Previously we were only talking about megabyte, then gigabyte, then terabyte, then now we are talking about petabytes. So in petabytes, 10 is power 15 bytes are there, and to see this magnitude, that it's not a number which is unrealizable, which is not being used. So if we look around us, then the amount of data which is generated in one day is 2.5 quintillions or 2500 petabytes. That was in 2018, so that means 2 years back. Now we are doing much more Facebook, we are doing much more YouTube. So the amount of data which is generated in big data schemes, because we are using clouds, because we are using the social media, and because there are IoT nodes which are very small and so many of them are there, each of them is generating a lot of data. So the amount of data generated is huge. Now we have to represent, we have to sometime count that, or sometime we have to write that data somewhere. So that means not only huge storage is required, but also we need to represent those large numbers. And it's not the question of only large numbers, but there are small numbers also. So for example, the size of transistors in the latest VLSI chips is around 7 nanometer. 7 nanometer means 7 into 10 is to power minus 9, quite small. And similarly, if we see the electron mass or anything which is related to quantum, the size is quite less, number is quite small. So that means the summary of this slide is, I would like to represent very large numbers like 10 is to power 50, 10 is to power 30. Also, I would like to represent very small numbers like mass of electron. So I have two problems in hand now. First, I would like to have a scheme of representation which can represent very large number as well as very small number. The second thing is, the decimal point should be represented in such a way that it is dynamic in nature. It cannot be fixed point like the previous representation of fixed point, where I need to have lot of memory, lot of bits to represent one small number. Because I can always spare more number of bits, but later I have to do computation also. And also, you see, let's say this large weight, we haven't written rest of the 21 digits here because we see they are insignificant, and we are worried only about the significant digits, and we have taken only 4 significant digits here. Okay, so although this number of atom here written is 0, so I'm not sure whether it is actually 0 or it is approximated. Yes, so what I mean to say, that we would like to represent these numbers, but not in an absolute sense, but in a relative sense also it will work. So how to represent such kind of a large numbers with the point which is not fixed? We call that floating point. Means the decimal point is not at a fixed location, but it would move along with the computation. So how do we do that? I suppose that something is coming in your mind. Yes, we use scientific notations as it is written over here. This is a scientific notation that you have, you are writing some number, then into multiplication, and then you are writing an exponential symbol. So the way we are doing it in decimal system, in the similar way we can do the same thing in a binary system also. So in a binary system, if I would like to do, then I have to use these scientific notations which are normalized. So let's spend some time on understanding what is normalized, although all of you understand that, but this is for the revision's sake, that let's say this is a number in a decimal system, 0.5 into 10 is to power 6. Is it normalized? No. A normalized number will have a non-zero significant, only one digit before decimal point. Before decimal point there has to be one non-zero digit, and after decimal point there could be anything, any number of digits could be there, but before decimal there has to be one non-zero decimal digit. So that means this number has to be written as 5.0 into 10 is to power 5. Why normalized forms? Because otherwise there would be so many of these notations and all of them would be equivalent. So that means the same number can also be written as 50 into 10 is to power 4 or 500 into 10 is to power 3. Okay, so to avoid all of those different forms which are actually infinite in nature, rather than that we say only one standard form. In a standard or a normalized form there would be only one non-zero digit before decimal, and after decimal in the right of decimal there could be any number of digits which could be 0 or 1. If we are writing 0, that means they are showing precision. If so that means if we are writing 0, they are also significant in nature because they are showing the precision. Now in case of binary, how it would happen? In binary also there would be like for example this is the number 1.00010000001. So if this number I want to represent as a exponential form or a scientific notation, then it has to be 1.000001 into 2 to the power 5, because this has to be 6, 2 to the power 6, so we can correct it. So this is actually 2 to the power 6. Now this particular way of representing a real number satisfy most of our requirement with a small exponent, not a very large exponent. So the examples which we have seen in our previous slide, they were talking about 10 to the power 20, 10 to the power 30 as the largest numbers, and that's actually the largest number. Now those, because it is in exponential form, I would require very less number of digits, a very small number here to represent that. The other thing, it can represent very small number as well as very large number. Large number means the exponential power would be in positive. In a very small number, that means exponential power would be in negative. So I can represent very large number, very small number, as well as I can control the precision. Precision could be fixed. I know that how many precision bits are there. In fixed point number, that was not the freedom I have. I only had like how many digits I can have. Here I can precisely choose. I can choose at how many precision bits I can keep in this normal notations or scientific notations. So this looks like a good way to move forward and represent a floating point number. But again, we are asking this question multiple times, but this question would be asked again here, that now how we will represent it in binary. We don't have a notion, we don't have a symbol to represent dot. and here we are introducing two more symbols in a decimal system. One is the multiplication, another is the exponent. So this luxury was there in decimal system that we can keep on introducing new symbols. So here we have in addition of decimal, we have these two new symbols. So basically I would require not only 10 symbols of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but also require these three additional symbols of point, multiply and power. So what is the alternative? So this alternative is the question which we have to answer. And if we are able to answer that question, that means we can represent our numbers. Yeah, so additionally one more thing, it's not only these three, but there is also two more, which means whether this particular number could be positive or negative, and similarly this exponent could also be positive and negative. So that means I need to introduce plus as well as minus. So 5 symbols are there. So I need to represent these 5 symbols in binary. Then I would be able to do it, represent these exponential notations in binary.